The diagram shows the plan of a school running track. It consists of two straight sections where which are opposite sides of a rectangle, and two semicircular sections, each of radius r. The length of the track is 300 metres, and it can be assumed to be very narrow. Part A, show that the internal area A metres squared is given by the formula 300r minus pi r squared. So the area of this shape is going to be the rectangle plus the two semicircles, which can be thought of as one big circle. If you take the area of this semicircle and this semicircle and add them together, then you just get one circle. The area of the rectangle, or the base, I'm not sure what the base is here right now, so I'll just call that x for now. I know the height of the rectangle is going to be 2 times r, because the r is the radius. So the total will be 2r. So the area of this rectangle is x times 2r, or 2xr. The area of the circle is pi times the radius squared. So that's my initial expression for the area of this shape. Some other information I was told in this question was the length of the track, so that's all the way around the outside. So all of this, plus this, plus this, plus this is equal to 300. So let me write that down. We've got, this is x, so that's 2x, plus, well, this is a semicircle. This is a semicircle, so those two things together will just be the circumference of a circle, which we know is 2 times pi times the radius. So this is my expression for the length around the outside of the track, which I'm told is equal to 300. Now that's useful because what I can do with this is I could rearrange to make x the subject. Remember, x is just the length of the track that I made up. So by making x the subject here, any time I wrote x before, I can now replace it with 150 minus pi r. This x here in particular. So expanding that out then, the 2 times 150 is 300, multiplied by the r is 300r. We've then got the 2 times the minus pi r is minus 2 pi r times the r. And then not forgetting the plus pi r squared on the ends there. These are like terms, so can be added together. And this is what we needed to show. So that's part A of this question done. In part B, it says hence, so using what we just did, find in terms of pi the maximum value of the internal area. We do not have to justify that the value is a maximum. Right, I'm just going to clear my screen to get a bit of space here. So press pause if you've not got this copied down yet. Right, I know that the maximum is going to take place when the derivative is equal to 0. So when dA by dr is equal to 0. So I'm going to take this expression for the area and I'm going to differentiate it with respect to the radius. The 300r will differentiate just to be 300. The pi r squared will differentiate to be 2 pi r. And like I said, that is going to equal 0 when we have a maximum. I'm then going to rearrange this to work out what r would be in that case. So I'm going to add the 2 pi r to both sides. I'll divide both sides by the 2 pi, which I can simplify a little bit because the 300 divided by the 2 is 150. So when the radius of this running track is 150 over pi, we will get a maximum value. The question wants what is the maximum value of the internal area, so I need to take that and substitute it in to work out what the area is actually going to be when the radius is 150 over pi. The question does want the answer in terms of pi. So when we do that then, the 300 times the 150 over pi gives 45,000 over pi. The 150 over pi squared gives 22,500 over pi squared, which when multiplied by the pi at the front will cancel to just be 22,500 over pi. The 45,000 over pi minus the 22,500 over pi is 22,500 over pi. And that is the exact value of the maximum internal area.